Okay, I think it's time. Good afternoon. Thank you for coming. According to the conference website, 23 people registered, so I can't start until all of them are present here. I'm kidding, sorry. No, it's good enough. If they don't come, they don't come. They miss. So I am going to talk about high availability in Postgres today. My name is Nick Ivanov. I work for Enterprise DB, probably one of the biggest contributors to Postgres and the corresponding tools. I work for a professional services branch in the company, so we deal with the customers every day and design and implement high availability solutions for them. So my talk is not going to be deeply technical. Instead, I will try to approach it as we would approach our conversation with the customer when we are asked to design a high availability solution, what goes into that solution design. So here's the outline. I will first try to explain to you what high availability is and what we think it is. Some of the methods that Postgres offers that allows you to achieve the required level of availability. We will talk a little bit about HA automation. I'll look at some typical deployment scenarios, and then I offer some tips for the time after you have deployed. So just so I understand, how many of you run Postgres today already? All of you, okay. And HA solutions, clusters, replication? Okay, half. Okay, fair enough. So first of all, a little bit of terminology, because the word cluster is being overused and it's not always clear what people are talking about when they say cluster. So in traditional terminology, Postgres cluster is a single instance or a single Postgres process managing a cluster or a group of databases. But when we move towards high availability solutions, the cluster also means a group of servers, each of them independently containing a traditional cluster of databases. So to avoid that confusion, when I say cluster, I mean many computers. And when I mean a single computer with a single Postgres process, that would be an instance, so that we don't mix it up. And also, the presentation, the copy of the presentation will be on my GitHub page, so you don't need to take pictures if you want to, so you can always grab a copy there. So what is high availability? It's a quote that nobody actually said, but it's loosely based on what Wikipedia thinks about it. It's a feature of a system that reflects its ability to keep up a level of operational readiness or performance in some adverse conditions, and performance should be above a certain threshold. Then you can say it achieves the availability that is high enough for the case. So high availability is always context specific. What is high for you may not be nearly high enough for the next person. So you always have to look at what it is that you want to achieve by configuring highly available system. So you need some measure. Frequently, people use uptime for the measure of high availability, which translates into things like 5 nines, 3 nines, which is sometimes misleading. There are a couple of related concepts that also allow you to measure the level of the highness of your availability. One is a recovery time objective. That is how much time you can spend recovering your system after a failure to the original state or to the original level of performance. And the second one is recovery point objective, which essentially determines how much data you can potentially lose as a result of the failure and still continue functioning. So there's a little graph that sort of visualizes these two concepts. So the X obviously marks the spot where something has failed, and the green bar is when your system operates normally. So the gap between the failure and the moment it begins to again operate normally, that's your recovery time. So your objective is to shorten it. And similarly, the gap between the moment of failure and the time going back where the data might be lost just prior to the failure is your recovery point objective. So your goal is to squeeze that also to the minimum. The database may be highly available by itself, but it does not exist in isolation. It's part of the often complex landscape of bits and pieces that all constitute your business application. So you don't measure normally the database uptime or availability isolated from all the other components, because if something else in your infrastructure is less highly available, that's what determines your system availability level altogether. So for this reason also, the number of nines or the uptime is a misleading measure, because you don't always know how it's measured. For example, you take 5 nines availability, which is a holy grail of designers. They say, oh, we can achieve 5 nines of availability. What does it mean? It means that in a year, a system can have at maximum 5 plus something minutes of downtime. But is it okay if you have all this 5 minutes spent in one day, like during the Black Friday shopping period? Maybe not. So if on average it works, it may not work for you in the moment. So from that point of view, RTO and RPO is probably a better measure, because it will give you the response time of your high availability solution in any given instance of failure. So how do you achieve high availability? Essentially, everything in life fails at some point. There's nothing eternal. So you can be sure that every component in your infrastructure will fail. So the only way to sort of react to that is to provide a spare. You could provide the spare by building a super reliable server that has multiple redundancy of every component possible. It will cost you a lot, and it will be reliable, because even if the power supply or processor or even main memory fails, there is always something that will replace it locally. But it is still vulnerable to a site failure. So if your data center goes down entirely, then no matter how reliable your server is, you're still down. So the other approach is you keep multiple copies of things. You keep your old small server here, another copy of that there, maybe a third copy somewhere else, and then also have a backup just in case. So now you have a problem of trying to synchronize your data across all these duplicate components. So that is another dimension of this duplication. And then another problem is you have all these spares, but you don't ever use them normally. You use them 5 minutes in a year, or in 2 years maybe. So, but you still have to pay for managing them, administering them, supplying electricity, air conditioning, all the other fun stuff for it. So the design of your high availability becomes a balance between the cost of keeping all this redundancy and the cost of losing productivity if something fails. So it's not even a technical decision, it's a business decision that people who write checks should make. So when you approach somebody who needs to make that financial decision, you probably want to present few options to them with different level of availability and different costs associated with it, so that then they can make a more informed decision about how much they're willing to spend on maintaining high availability. So that's something we learn on the job. Like we want to say, oh, this is the best possible approach. It will have not sub, but maybe the failover time in 2-3 seconds and zero data failure, zero RPO. But it will cost you. And then the customer would say, we don't need that. I mean, we can live with the system being down for half a day, nobody complains. So then you don't need probably all this high availability. You're just fine with the backup. So this is why I'm listing the backup as a high availability solution, because ultimately it is. It is a copy of your data stored somewhere. And if the RTO and RPO that your backup can afford you is satisfactory to your business requirements, that's fine. That's your high availability solution. You don't need to pay for anything else. And then there's variation of the backup with the associated wall archive with it, which allows you to limit RPO and probably RTO as well. Then there's physical replication, which is the next step up the ladder. Then there's logical replication. And then there's the ultimate Postgres-based solution with active-active clusters where you can bring both RTO and RPO practically to zero at the cost of running. So I'm not going to, yes, please.
When we use the physical and logical, when we use the logical replication and the physical replication?
The question is when we use physical versus logical replication. We'll come to that. There's a discussion later in the game here. So I'm not going to spend much time about the backups because you all know what that is. Basically, I'll pause here because that is a precursor to physical replication, essentially. So point-in-time recovery is when you have your base snapshot of your database plus a collection of wall archives between the time of the backup and the moment of failure, hopefully. The comment here is that the export and import is also a way of backing things up. Yes, it is, but it's so off the chart in terms of RTO and RPO that we probably don't want to waste time discussing it. But it is an option. Yes, you can dump your data with PG dump and live with it. So with point-in-time recovery, you now need to juggle the combination of not just the base backups, but also the walls that belong to each specific backup, because they are not by themselves meaningful without the base backup that they belong to. So now it becomes a little bit problematic for a person to manage, and there are tools that allow you to manage recovery objects together, such as Barman and PG Backrest, two very popular solutions. And Barman brings you very close to replication because it has an option of streaming your walls to the archive it maintains, so that it is almost a physical replica in the sense that everything is there except the running Postgres instance that manages it. but it's there. So when you move to physical replication, you simply, to that picture of the copy of your data, you also add a copy of your server, which together now allow you to run a system that is continuously being restored to. So this is what physical replication is. It is a never-ending restore. And when you need to fail over, you just finish that restore and activate the database. That's what it is. So there are two ways of managing a physical replication in Postgres. One is this traditional log shipping. The other one is streaming replication. So with log shipping, you have an intermediary system between your primary and the replica that stores your WAL archive files. So the primary sends the WAL files to the archive when they are rotated, and the replica periodically connects to the shared storage and retrieves those files and applies them locally. So in this case, your RPO depends on the frequency of your log archiving. Normally, it's like 5 minutes. So in case of failure, if the primary didn't send the latest WAL, then the replica will be 5 minutes behind the primary, obviously. You can tweak the frequency of archivation, but that would incur additional cost on the performance of the primary server. This is by definition an asynchronous process, so that means that you cannot possibly achieve zero RPO with this setup. And your standby can be hot in the sense that it can serve read-only workloads. With streaming replication, you remove that intermediary. You instead connect the replica directly to the primary and allow it to pull WAL records as they are being generated. So every commit sends a WAL record to the replica, which is immediately applied. So your RPO is reduced to the latency of this traffic between the primary and the standby, plus a little bit of overhead in writing the data on the disk. So this is asynchronous by default, but you can make it synchronous such that the primary would not consider the transaction committed until it receives a confirmation from the standby. So this means your RPO is practically zero with some caveats, but you can effectively treat it as a zero RPO. And it requires a privileged connection from the replica to the primary, essentially because the replica reads your WAL file, which contains all the sensitive data in your database. So you don't want to allow just anybody to use that protocol. So this shows just basically a local or a DR setup where you have a primary in one side and the replica in the other side. But you normally want to improve your posture of high availability by allowing you both local and remote high availability. So you would maintain replicas in your local data center along with your primary, plus some replicas in a different region or location as appropriate for your DR strategy. And in this case, a question.
So, but as far as the user, he can only use one of those databases, right? Or turn the other read-only?
The question is if the users can use all of the database instances or just the primary. So they can write and read the primary, and they can read the replicas with some tricks that we will discuss a little bit later. Because allowing people to read on the replica may affect your data consistency and respectively RPO. So for the cases where you have multiple replicas, you may want to consider what we call a cascading replication, where the remote replica in a different region is the only one in that region that connects to the primary, which reduces the workload on the primary, reduces your intra-region traffic, and primes that cascading replica to become a new primary if your original region fails. So cascading can be done in many levels, so you don't have to cascade all the replicas from the primary. You can cascade some replicas from the cascading replica, so you can multiply that picture almost indefinitely. And now we're coming to the logical replication as the means of maintaining database replicas. In contrast with the logical replication, where what you ship to the replica is essentially a wall record, a binary image of something that's changed on the database. With logical replication, there is a thing called decoder that translates this wall record into something of a higher level. It's not exactly the insert, update, delete statement, but it is a message that corresponds to the insert, update, and delete on the replica. So instead of blindly making a binary copy of the primary data on the replica instead interprets what it receives from the primary and applies that change locally. So it allows you more flexibility in what you replicate. For example, you can select a subset of tables from the primary that you want to apply on the replica. Or you can filter by rows, by row conditions or columns that you want to receive, right? So with physical replica, all the databases on the primary share the same data directory and the same wall file. So you replicate everything that happens on the primary instance, not just one database, all of them. With logical replication, obviously, you can limit the replication to a single database. And obviously, since the logical replica is not being in recovery, it is just a normal Postgres instance, you can write to it as well. So now becomes a possibility of conflicts. You update something on the primary, but then you update the same thing on the replica. So what to do with it? Nobody knows, really. I'm talking about the built-in logical replication in Postgres, right? Logical replication cannot replicate DDL statements. So if you change the structure of something on the primary, it's not going to happen on the replica. So if you do that, it's a practical guarantee that you break your replication, because if the structure of the table is different, no inserts or update will happen on it, and subsequently the replication will stop because it will not jump over the failing replication message. So for this and some other reasons, built-in logical replication is not suitable for an HA solution by itself. So some people tried to build bidirectional replication based on built-in logical replication, but it didn't quite work well because, as we said before, no DDL replication, no conflict resolution. Failovers become very difficult because replicas have all their own wall streams with different LSNs. So by looking at the primary LSN, you don't know if that matches to any particular LSN on the replica. So if you fail, you don't know where to start from to replicate back. So you need to introduce an additional process that would track these transactions on all sides of the replication and kind of make a sense out of it. So that's why using the built-in logical replication is not practical to build an HA solution. So some people, including developers at EDB, thought of improving that situation. So there were a number of extensions developed for Postgres which try to implement a truly bidirectional replication system. So there's one thing that was called PG logical, without two in the end, which eventually became actually the logical replication engine in Postgres itself. But development of that continued into the PG logical 2, which was very close to allowing you to do a bidirectional replication. But it was kind of stopped. So this project is not really maintained anymore. Instead, some people who originally worked on that project inside EDB created something that was called originally BDR, or bidirectional replication extension, which is now renamed to Postgres distributed. So that is a truly bidirectional replication system. Also, another group of people took that same base code and came up with a product called PG Edge, which is a company in itself, and it's fully open source and also offer a very similar option of bidirectional replication. So if you compare all these options that we discussed in terms of which levels of RPO and RTO that they allow you to achieve, the loser here is obviously the restore, because it does not let you have any acceptable RTO or RPO numbers. With a log shipping replication, you're getting close to your RTO target, but RPO is still high because it's essentially determined by the frequency of log archiving, which is almost always not acceptable for a very high availability, highly available system. So now then you have your streaming physical replication, asynchronous versus synchronous, which allows you the failover times of approximately, in practice, often under 1 minute, but in most cases over 30 seconds, because you need to do a lot of stuff to convert the database from the being restored into a database that can accept read-write traffic. And the active-active systems based on the logical replication, as I mentioned, these extensions, they truly allow you to bring both RTO and RPO targets to almost to zero. Questions? Yes, the question is whether BDR can do DDL replication. The answer is yes, it can, with some limitations. Not every single DDL statement can be replicated, but most of them are supported, yeah. And the same is the case for PG Edge as well. Anything else? Nope. Okay, some fun deployment examples. What's missing in this picture? We have a primary, we have a replica. Is it a good, say again, sorry?
So how's the data getting replicated?
Well, it's a physical replication system. You have a primary and you have a streaming replica which receives the wall stream, and it replicates, and it's up to date as far as it can be. So what happens when the primary goes down? The replica remains a replica. It sits there, it potentially serves read-only traffic, but it doesn't know anything about the primary, except that it cannot connect to it, so it just stays there. So if you need to fail over, there's a number of things that you need to do to restore your system, even if you have a replica ready. You need, first of all, to detect the failure and determine that it is actually a failure, is not something transient like a network glitch that goes away. Now, if you have multiple replicas, you need to figure which one of them is closest to the primary in terms of LSN that it can be promoted in advance of the others. You need to fence off the old primary in case it goes up. It must not be allowed to become a primary again, because now if you do that, you have two primaries and you have a split brain and you have corrupted data. So you don't want that. You need to ensure that your clients now are connecting to the newly promoted primary. If you have multiple replicas, you need to make sure that they're reconfigured to connect to the new primary to continue replicating from where they left off. And then finally, when the old primary is recovered, it needs to be admitted back to the fold, but not as a primary, but as a replica of the new primary. So all these things you would need to do, or somebody. So, but you don't want a human to do this, because first of all, you wake up in the middle of the night, your RTO would be very low. So you want to automate these things. Client failover. How can you implement client failover to the new replica? First of all, there's a built-in mechanism in the libpq communication library of Postgres that allows you to specify multiple host names in the connection string, which the driver will then try in order. If it cannot connect to the first one, it will try the second one. So in the simplest case, after failover, if you list your primary and replica in that connection string, the first try of the driver will fail because the old primary is not there anymore, but the next try will connect to the old replica, which is now the new primary, so the connection succeeds. So you can use that as a client failover mechanism. If you have a proxy or a connection pooler sitting between your clients and the database, then you don't need to touch the clients. Instead, you reconfigure the proxy or the pooler to switch the target of their connection to the new primary. You can have a virtual IP pointing to the database. So you would need to reassign that IP to the new primary. And then also there are third-party load balancers, especially if you run on Amazon or some other cloud platform, you can reconfigure those to start talking to the new primary. So here come the solution to all this set of things that you need to do. A cluster manager, or what's often called a failover manager. Since you need to automate the process of doing all these things, you have a software tool that allows you to do that. So let's add the cluster manager to the picture. We have two instances of the cluster manager co-residing with the database instances, monitoring them, communicating with each other, knowing each other's status, replication status, log, everything. But something is still missing, right? So let's say something happens that the replica cluster manager cannot talk to the primary cluster manager anymore. Why is that? It doesn't know. Maybe it's just a network breakage and the primary is actually running. So in that case, I do not want to promote the replica because now it becomes the second primary again, split brain, data corruption, everybody's unhappy. But it may be the case that the primary actually failed. So in that case, you need to promote the replica. So how do you decide with this situation? You can't. You need an arbiter. You need a voice of reason sitting somewhere else to help you make that decision automatically. I mean, with this, you can introduce a human who would log into this site, and then decide what to do. So yeah, that's possible. But if you want to automate this fully, you need something that can maintain a majority vote in case of a single instance failure. So in this situation, we can decide that if both replica cluster managers see each other, but none of them see the old primary, it means that the old primary must be truly dead. And now they can elect a new primary candidate between themselves and promote it. And similarly, if the old primary cluster manager cannot see either of the remaining ones, it knows it's left alone. And even if it's just a network isolation problem, it would still not decide to promote to keep running as a primary to avoid this split brain situation. So this is the importance of the quorum in the cluster manager's setup, right? A question, yes?
So in this case, what happens if the primary is okay, but the cluster manager fails?
Well, depending on the cluster manager that you use, the answer will be different. So the question was, what happens if the cluster manager fails, but the primary database instance itself is still running? So like I said, the answer is different. Some cluster managers would bring the instance down with them, patroning, in most cases. So if I die, everybody dies with me, and the rest would be left on their own. So if there is a quorum outside, they will decide on a new primary, and that's it. Some will just die and let the primary continue running. So yes, it's not a happy situation. But this is really a rare scenario because the cluster manager is really a very simple piece of software. It doesn't just fail because it got tired of running, right? Something truly bad must have happened to the system. So probably if the CM dies, then probably everything else is also not in good shape there. But yeah, it's a very good question to ponder when you choose which cluster manager to set up. So expanding this quorum thing onto a larger picture where you have a primary location, a DR data center, if you want to have truly automatic failover in case of a site disaster, you still need to apply the same principle of trying to maintain consensus or majority in the cluster to that situation as well. In this case, if you don't have this bottom square saying witness, what happens if the network link between the two sites is broken? They are equal. They have equal vote, so they cannot decide that between themselves who is to survive. So you introduce an extra vote in the picture, so if the link between DC East and DC West fails, you still have this witness somewhere else that allows one of the remaining parts of the cluster to form the majority and therefore make a reliable decision of who to promote. So now going back to the question of what happens and why it's maybe different, because there are several options of failover managers or cluster managers for Postgres which you can choose from, and they all behave differently. So when you choose what to use, not only you need to look at what you're familiar with and what you don't like, but also whether it is capable of doing what you need it to do, because not all of them do the management part equally, well, I shouldn't say equally well. They do it differently. They take different approaches to how they decide who to promote, how to recover from the failure, and so on. So I am not going to dive into details about which one is better. I just tried to compile this table to show you various characteristics of each of them, which might help you to reduce your scope of search, so to speak, when you make this decision. So when I say configuration store, what I mean is an example of Patroni is that it doesn't store the cluster state inside the Patroni process itself. Instead, it uses an external distributed configuration store like etcd or other things that maintain the consistent distributed data store for them. So they rely on this additional component to help them make a decision, right? So if Patroni by itself without this DCS would not simply controls the local instance on each node. And if they cannot retrieve the information from the DCS or distributed configuration store, it means they are not operational anymore. So this is what decides on the majority in this case. So you don't have an extra instance of the cluster manager. Instead, you have an extra instance of the DCS software that provides the consensus support for them. The rest of them do maintain the cluster configuration inside, so they become both the configuration stores and the actors that manage the instances. In case of PG or to failover, you have to maintain an extra machine that runs a Postgres instance additionally to your normal data, which stores the configuration state in that case. It's not a bad thing by itself, it's just a feature, so you need to understand that that is something you need to take care of as well. Some of them don't support cascading replication. Some of them do not allow you to have a fully automated DR like we had in this 2 sites plus witness picture, because they assume everything is in a single site. So they treat the whole picture as a single cluster, whereas with DR, it's not quite like that. So only, as far as I know, only Rep Manager is capable of treating 2 sub-clusters the way they should be treated. Yep.
In terms of the top line, Patroni, Rep Manager, and so on, are those actually vendors, or are those extensions, or any
Yeah.
free, or you have to pay for it?
Yes, so this is on the second page. So the question was, what are those tools and how they are implemented? So some of them have an extension component in them. Some of them are truly external third-party products, like Patroni is essentially a bunch of Python scripts connecting to Postgres and etcd. Some of them have limitations in how they integrate with external components that help with client failover. And 3 of those are open source. Patroni, Rep Manager, PAF, they are all freely available. EFM is our own product, so it's a paid product, so it's not open source. They have different interfaces to control them. Some people like the fact that you can monitor your cluster manager through SQL, which is convenient. Patroni doesn't have the SQL interface at all. Instead, it offers you a REST API. Okay?
Saying monitoring through SQL, you mean you could actually set up a SQL witness? With a quorum, part of the quorum?
No, what I'm saying is you can't, since there is a an extension component to that particular cluster manager, some of the functions are available through the SQL interface. So you can query the cluster status by selecting from a certain view that the extension maintains. Or you can issue the function, call the function that would switch the roles in the cluster. It's not like there's a SQL witness in it. It's a kind of just an interface to.
API that you can
Yes.
from SQL
Yeah.
and run commands to actually, okay.
Yeah. So all those scenarios that I described, they apply equally to both clusters based on physical replication and clusters based on logical replication. So for logical replication, the same logic applies to having to have some sort of a cluster manager that does all this failover logic and other things in it. So since PGLogical 2 is not a maintained product anymore, I didn't include it here because nobody should really use it. But the two remaining products are very comparable in what they do. They both are implemented as Postgres extensions, and they both have this ability to determine the cluster status, maintaining quorum, doing the majority-based election between them inside that extension. So they're very, very similar in that sense. In addition to just having a cluster manager, the Postgres distributed from ADB also contains a connection routing proxy, which allows you to sort of direct traffic to either. So since it's an active situation, there is no primary and standby. They're all primaries all of the time, right? Because they're all in the same state from the point of view of data. But to avoid the risk of data conflicts, in some cases, you may choose to ensure that your read-write traffic only goes to a single node ever. In that case, there's absolutely no risk of introducing data conflicts since nobody updates any other nodes. So in Postgres distributed, the nodes elect a leader between themselves, which is designated the right target. So, and then there's a proxy that knows about this decision, and then it can route all the traffic from the clients to what is known as a leader internally. And by the same vein, it would then allow you to direct read-only traffic to anything but that leader. So that's just a little addition here. So both of them support DDL replication to a large extent. Like I said, there are some limitations and so on.
So the proxy does not act as the third part of the witness. The proxy does
Right. Yeah, so the question is whether the PGD proxy is part of the consensus. The answer is not. It simply reads the result of that consensus decision of who is the leader and then just acts upon it. So it does not vote. It's just a little network layer component that just switches the traffic between the nodes. Both of them allow you to run both asynchronous and synchronous replication. PGD is a little bit more feature-rich in that sense, but it's something that you may or may not need. So, but they both use the standard Postgres synchronous replication configuration to do that. In distributed systems, especially those who are active-active, biggest problem is maintaining the sequences, because sequences are local to each database instance. They're not replicated ever by the logical replication stream. So you can't really use traditional Postgres sequences in an active-active system, because they will, by definition, introduce conflicts. Because if you start increasing the sequence from 1 on this side, you will also start increasing them from 1 on this side if you start writing on that other node. So immediately you have a conflict. So in a distributed system that allows writes on multiple nodes, you have to choose some other way of generating unique values. In most cases, this is something like a snowflake ID, which is a sort of UUID time-based, which guarantees that the values will be unique across the whole cluster. But they're not always acceptable because they're very long. PGD has an approach to that where it maintains ranges of sequences that are different across the nodes. So this one has 1 to 2 million, this one has 1 to 2 million, 2 million to 4 million, that one has 4 million to 6 million, and then when they exhaust the ranges, they communicate between themselves to redistribute that ranges again. So PGD is not open source. PGH is, so choose whatever you wish. Any questions? Okay, so we have, yeah?
You're not finished, I assume, are you?
No.
The question I had is, in terms of you mentioned the proxy, yes, which acknowledges, so that'll be the quote-unquote automatic failover. How do you do the recovery to go back to, or do you just leave that one as the primary at that point? And then how do you reinstate in state or reinstantiate or
Yeah.
the actual failed old primary?
Yes, so the question how failover works in an active-active cluster, right? It's actually much simpler than it would be in a physical replication cluster because there's no primary and standby. They're all primaries. The notion of the primary in an active-active system is superficial. You decide who is the primary, and you write to it. So when the one that you write to fails, every other node in the cluster is exactly in the same state, and they're already active. So you can immediately reconnect to any of them and continue working. So how do you rejoin this one back depends on what failed. Like if it's just a system crash and no data is lost on disk, once you bring it back up, it will join the cluster, it will see where the LSN is on all the other nodes and just continue receiving replication stream from the other nodes. Because in an active-active cluster, each node replicates to each other node all the time. So it's not like one directional. It always goes in both directions. So
Would the recommendation be that you have these two nodes in a bidirectional streaming configuration? Or?
Same logic applies. If you don't want automatic failover, you are okay with two nodes, but two nodes cannot form a majority. If one of them fails, the other one doesn't know what to do. So,
I was thinking in terms of Microsoft where you have the file share witness.
Right.
It can be a UNC path that both of the nodes could actually
Yes.
So, and then now they've introduced an automatic. So if there are 4 nodes, it will utilize the file share witness. If there are 5 nodes,
Yeah.
it disables it for that
Yeah,
connection.
yeah.
So I'm not sure if that's the same mechanism, and that's why I was asking about the proxy then, if it
Yeah.
acted as the quote-unquote witness, because I'm assuming the proxy does not reside in either of the 2 nodes.
well,
So it's
yeah.
What application service? It's an application front end?
Yeah, so the question is too long to repeat, but it's basically tries to draw analogy between the SQL Server AGs and say the logical replication clusters here. So the answer to the first part of your question, how the quorum is maintained, there's no notion of the file witness in this system because Postgres doesn't support file witnesses, but at least a Postgres distributed has a notion of a witness node, which doesn't have the application data. It has essentially an empty Postgres instance with the extension. So it doesn't participate in replication,
Correct.
but it sits there to provide a witness function in case something fails.
So you have to have a third Postgres installation with the actual extension installed.
Yes,
which
but
acts as the witness.
Yes, but no data and no
Interface with
replication.
the
Yeah.
actual proxy.
Well, the proxy reads this cluster state from any node because it's distributed across all nodes, so it can connect to anyone and see who the boss is in there, right? And it doesn't have to reside on the same machine as the Postgres nodes. It could be somewhere else. So it's a purely network layer switch to direct the traffic. So it does not participate in any decision making. It accepts a decision made by the Postgres nodes in the cluster. So it is like a very lightweight HA proxy, I should say, without any logic in it.
And EDB, is that as used for both Windows and Linux?
No, unfortunately, Postgres distributed only supported is on Linux and other
You're
Unixes.
getting my hopes up.
Well, I'm
Because
sorry.
I could just install Postgres on a Windows server and a SQL server, right?
Yeah.
And then utilize that because I'm not really using it for anything except for monitoring the actual.
Yeah, well, I'm sorry. No, we can.
You should have said that up front.
Yeah, well, I mean, it's possible if there's enough interest, but so far we haven't seen any significant interest in running this on Windows only. In my 2.5 years at the company, we only just recently had a single client who asked us to install Postgres on Windows. Single client out of hundreds. So, in closing, a little bit on the surface of what to do when you have your cluster running. Replication security. Replication stream contains all your data. So you want to protect the traffic. Use SSL. Certificate authentication between the nodes. It's not always easy when you have many clients, so you have the headache of managing the certificates, but for replication it's much easier because you have only a limited number of nodes that you need certificates for, so it's probably advisable to use certificate authentication for just replication. And don't use super user privileges for replication. You don't want to mess up with the primary if something goes wrong, so there's specific replication privilege which is high enough to allow you to replicate, but not high enough to mess things up. Performance. Obviously, you want to have all your replicas to mimic the primary in terms of hardware, because you don't want to deal with performance problems after you fail over and suddenly something just doesn't scale well enough. So goes back to the cost of maintaining replicas. Ensure that you have enough configuration settings for worker processes and replication slots, because the default may not be enough if your cluster is more than 2 nodes, right? So keep this in mind. Wall compression is not turned on by default in Postgres. You should turn it on because it really does help with performance of reading the wall files and writing the wall files. And if you have many nodes, writing happens many times. So to reduce disk I/O, use compression because it drastically reduces your hardware dependency on that case. It does cost some CPU cycles, but not much. Replication breaks. If the replica stops, it relies on the presence of the wall files on the primary. But primary has to recycle wall files periodically lest it runs out of space. So if your replica stays down long enough, it may happen that when it tries to reconnect, the walls that it needs are already gone. So either provide enough space by setting up these parameters, or make sure that you start up the replica soon enough so that you don't need to. But there's a downside to this. If you keep walls for long enough, you will run out of space on the primary, which will bring the whole server down. So you don't want to exceed that threshold either. And here we speak about monitoring the replication. There's several built-in views in Postgres that show you the replication status, which LSN has been sent, which LSN has been received, applied, and so on. So you can monitor the lag of your replication as it goes, but you need to remember that replication lag metric is approximate. It's not the last truth. It is an average over time. So if you see the number that you don't see a replication going on at all, so no changes on the primary, and yet you see the lag above 0, that's because we have an average from some time before. And until you start moving things forward, that average will just remain the same. So the fact that nothing happens here but lag is above 0 is not a case for concern.
Is it similar to log shipping or not?
It's applicable to both. I mean, with log shipping, your lag would be bigger because you apply the walls in chunks instead of one by one. So you have the lag of your whole wall file for some time, then you apply the whole log wall file. It goes down to nearly 0, and then it begins accumulating again and goes down again. So with
Is the wall file generated per database, or if there's 3 or 4 databases on a cluster, is it for all the databases?
yes. So the question is whether wall file is specific to a database or the entire instance. The answer is the latter. In Postgres, wall is instance level file, so you cannot isolate database wall files. Everything goes in the same pile. And this is also the reason for some people being surprised when especially in logical replication, where you configure subscribers to replicate specific databases, and you update one database on the primary, but wall senders for every database begin reading the log, but only one replicates. All the others, reject because it does not apply to my configuration, right? So there are some things that may look strange because of that globalness of the wall file.
And streaming then is likewise the same, or is streaming per database?
Yeah, the question is whether streaming is per database. No, again, it's the wall file that is global, so I cannot stream.
Okay.
I can only stream what I choose, right, from that global wall file. So if I have a logical replication configured to only replicate data for specific tables in a specific database, I still have to read this whole wall stream to pick only the things that I want to replicate. So this applies to logical replication. With physical replication, I don't look inside the wall. I just throw everything over the fence and let the replica figure it out. And the replica doesn't figure it out. It just applies everything in one shot, which is why DDL works with physical replication without any limitations, because I just take an image of this disk and ship it there, and that's it. Well, not exactly the disk, but more or less. Any other questions?
Is a standby database is part of replication?
Is the standby database part of replication?
Yeah.
I'm not sure what.
Oracle will have standby is part of DR, disaster recovery. Replication is different.
The replication, whether it's different with standby or not, is a question, is a topic for debate. I personally don't make this distinction. I don't care where my replica is, whether it's in a DR site or it's in my local data center. For me, it's just a replica. So I don't really know how to make the distinction between the replica and the standby. To me, they're the same. So you choose the method of maintaining your replica, and then that's the method you choose. So if what you're asking is whether you can combine physical and logical replication, then the answer is yes. You can, for example, have a logical replication set up in your primary data center and also maintain a physical replica of one of the nodes here in your DR data center, which makes your DR process a little bit more complicated because now you need to promote it, rebuild a new cluster there. But yeah, it's doable, so you can combine the two, but I don't really know how otherwise to distinguish between the word replica and the word standby database. To me, it's all the same. Maybe I'm just not understanding the SQL Server-based differences in terminology. So this is Q&A. It was, yes. So we're out of time, but I'm still here. So if you want to talk about this some more, I'm happy to do that. Thanks for coming. Give us feedback, and me will be very nice to know what you think about what you heard. And like I said, there's a link to my GitHub. The presentation will be there, so you can grab it.
I noticed the 2023, but not to tell you, I didn't see a 2023. Maybe you had.
I was there. It was about Kubernetes, not.
Right, but I mean, I didn't see the 2024 presentation yet.
Yes, we're asked to put it after the session.
Oh, okay.
So
I'll be following along with you.
yes. So it will be there in about 15 minutes.
I caught you out on both accounts.
I know, yeah, well.
That was great. Thanks, Nick.
No, thanks.